Our wine model had an R-squared value of 0.83, which tells us how accurate our model is on the data we use to construct the model. So we know our model does a good job predicting the data it's seen. But we also want a model that does well on new data, or data it's never seen before, so that we can use the model to make predictions for later years. For this particular application, Bordeaux wine buyers profit from being able to predict the quality of a wine years before it matures. They know the values of the independent variables, age and weather, but they don't know the price the wine will eventually sell for. So it's important to build a model that does well at predicting data it's never seen before. The data that we use to build a model is often called the training data, and the new data is often called the test data. The accuracy of the model on the test data is often referred to as out-of-sample accuracy. Let's see how well our model performs on some test data in R. We have two data points that we did not use to build our model in the file winetest.csv. Let's load this new data file into R. We'll call the data frame wine test, and we'll use the read.csv function to read in the data file wine_test.csv. Make sure you're in the folder on your computer containing this file before using the read.csv function. If we take a look at the structure of wine test using the str function, we can see that we have two observations and the same 7 variables as before. To make predictions for these two test points, we'll use the predict function. We'll call the output predict test, and we'll use the predict function using model 4, our model with the 4 independent variables, and then we need to indicate that the new data that we want to make predictions for is in the data frame wine test. If we take a look at our predictions, we can see that for the first data point, we predict 6.7689, and for the second data point, we predict 6.6849. If we look back at our str output, we can see that the actual price for the first data point is 6.95, and the actual price for the second data point is 6.5. So it looks like our predictions are pretty good, but we can quantify this by computing the R-squared value for our test set. Recall that the formula for R-squared is 1 minus the sum of squared errors divided by the total sum of squares. So let's start by computing the sum of squared errors on our test set. We'll call it SSE, and we want to use the sum function, follow that with 2 left parentheses, and then the actual price values, wine test, price, minus our predictions, predict test. Close the first parenthesis, and then type the caret symbol and a 2 to square these, close the second parenthesis, and hit enter. Now let's compute the total sum of squares, which we'll call SST. This time, when we take the sum, we want to compute the differences between the actual values, wine test price, and the mean of price on our training set. Again, square these values and sum them up. Now, to compute the test set R-squared, we can just type 1 minus SSE divided by SST. So the R-squared on our test set is 0.79. This is a pretty good out-of-sample R-squared. But while we do well on these two test points, keep in mind that our test set is really small. We should increase the size of our test set to be more confident about the out-of-sample accuracy of our model. We can compute the test set R-squared for several different models. This table shows the model R-squared and the test set R-squared for the linear regression model as we add more independent variables. The model R-squared will always increase or stay the same as we add more independent variables. However, this is not true for the test set. When selecting a model, we want one with a good model R-squared, but also with a good test set R-squared. It looks like our model that uses average growing season temperature, harvest rain, age, and winter rain does very well on the training data and on the test data. But for this example, we need more data to be conclusive, since 2 data points in the test set is not really enough to reach any conclusions. Also, note here that the test set R-squared can actually be negative. The model R-squared is never negative since our model can't do worse on the training data than the baseline model. However, our model can do worse on the test data compared to the baseline model, leading to a negative R-squared value. We'll see in the next video how well Ashenfelter did using this model to make predictions for later years.